Okay, welcome everyone. So my name is Will Robertson, and this is Ahmet Buyukkayhan, and we're going to be telling you about automated detection of Firefox extension reuse vulnerabilities. So before we kind of dive into the material, a little bit about ourselves. So speaking for myself, I'm an assistant professor of computer science at Northeastern University out in Boston, Mass, back in the US. Where I co-direct the Northeastern System Security Lab with Engin Kirda. So I've been, working in academia for a while now, so publishing since 2003 in the areas of systems, network, and software security. And I actually have a bit of a connection to this community. So I was a founding member of Shellfish, which, was a DEF CON CTF winner way back in the day. So I'm very excited to be here to tell you about some of the stuff that we've been working on lately.
And I'm PhD candidate at Northeastern University and member of Northeastern University System Security Lab. And I also like to play CTF, but I'm not an official member like Will. And you can continue.
Cool. So, just to say a little bit about the venue, I mean, this is an amazing place. This is our first time to Singapore, and, everything's been great, but, especially the weather, because usually around this time of the year, Boston looks something like this. So believe us when we say we're very happy to be here. So in terms of the agenda, it's going to go something like this. So I'm going to give you a bit of background to kind of set the stage for why we think these attacks are kind of relevant and interesting. Before going into the, high-level sketch of what these attacks actually look like. From there, Ahmet is going to take over and show you the tool that we developed to find these attacks on against Firefox, and then do a bit of a demo to show you how this all kind of fits together. Finally, he'll tell you a bit about, this evaluation that we performed to kind of measure the significance of the problem. And then we'll conclude with some final, parting thoughts on where things stand and where things might go in the future. Okay, so without further ado, extensions. So I'm not going to tell you, browsers, right? Because, everyone is using these things every day, right? They're many see browsers as really the next computing platform for developing and deploying apps. I mean, you just need a browser, and anyone can access your centrally deployed and updated application. So browsers are great, but early on, people recognize that, hey, it would actually be a great idea if we could, allow users to add new capabilities to browsers or customize them. And, so Firefox was an early mover in this space. And indeed, if you look at the Mozilla add-ons repository, you'll see that there are a large number of different extensions that users can download and use to, modify the behavior of Firefox in some way. So about, 15,000. Up on the slide is AdBlock Plus, which I'm sure many of you have installed. There's some variant of this which, greatly improves the user's web experience. And also incidentally serves as a great way to, cut off one of the major attack vectors against browsers today. And if you look at popular instances of these extensions, you'll see that many of them have millions of users. So there are significant user populations that are using extensions, and if these extensions are, buggy or malicious, there are significant amounts of users that could be exposed to attacks. The final thing I'll say, in this kind of first slide is that, at least for Firefox, the vast majority of these extensions are written primarily in JavaScript, not always, right? So there are cases where you can have components of these extensions developed in native code from C++, but by and large, most extensions are primarily written in code in which both Mozilla and users could, in principle, manually inspect, right? So there's a lot of visibility into the inner workings of these extensions. So, as a first mover, as I said before in the space, it's always nice to be the first mover, but at the same time, Mozilla had the somewhat unenviable position of trying to anticipate, all the kinds of attacks that might occur, as well as more generally, not really knowing how extensions would be used by users, right? So they put forth this very flexible programming model, right? So what does that mean? Well, if you look at how the legacy or first generation Firefox extension architecture looks like, you have a couple of key characteristics that we make use of in our work. So first of all, there's this shared JavaScript namespace. Now, what does that mean? Well, that means that extensions that exist in the browser can read and write objects or variables or any other data that's exposed by other extensions. There's no isolation going on. That's a big deal, right? And moreover, right, if you have an extension, it can directly invoke or indeed even change the code of other extensions. So that's an important thing to keep in mind. There's also this shared GUI. There's shared GUI state, right? So a shared window. So that means that all extensions have full access to the window and is able to modify the UI. And so if you're thinking already, well, that sounds great for UI redressing and spoofing attacks, well, you're right. Moreover, extensions can listen to all events, right? So they can register event handlers and intercept any events that are coming from the user. So this is also a very nice capability. And finally, in the legacy extension architecture, there's absolutely no privilege separation, right? So that means there's no sandboxing of these extensions, and so they really have full access to the resources provided by the underlying system, right? So that means full access to the file system, or full access to contact arbitrary endpoints on the internet. So these are all very strong capabilities provided to extensions. Really, they have the full capabilities of the browser itself. So, let's think a bit about what the threat model is in this setting, right? So, clearly the browser is a very attractive target. So many of us are using the browser to, manage our finances or talk to people via social networking and all that sort of thing. And so we have a lot of trust placed in the browser vendors, and so we assume that, hey, there's no backdoors being inserted by browser vendors and all of this. But, if you think about it, if you kind of squint your eyes, right, the extension API really is kind of a backdoor to allow potentially untrusted third parties to run code in a highly privileged context, right? So, extensions can be written by anybody, and all they have to do is convince you, hey, you should install this great extension. So, we trust the browser vendor, but we really shouldn't have that much trust in the authors of these extensions. Well, how can these extensions go wrong? Well, I mentioned before, there are kind of two separate threat models, right? There's the first one, which is vulnerable extensions, or also known as the benign but buggy threat model. And, well, nobody is formally verifying that these extensions are free of vulnerabilities and, are following some spec of, good program behavior. So, as with any software, they can have bugs that have security implications and could be exploited by other malicious, parties. So, that's a problem. And most of our defenses are often oriented towards this. But there's also this problem of malicious extensions. And these are a real threat, actually. So, up on the slide, you can see that there's actually a blacklist maintained by Mozilla against a number of malicious extensions as of, February 2016, 161 malicious extensions. And indeed, malicious extensions are a huge topic of study in academic circles right now. So if you think about extensions attacking, say, password management in the browser, which lots of people use the browser for, that's something that occurs. Google performed a nice study last year where they showed that ad injection is on the rise, right? And this is an attack where extensions are diverting ad revenue from web content publishers to the authors of extensions, or maybe people that are paying them by either replacing or simply injecting new ads into certain sites when the user browses to them. So in general, the basic idea of this sort of attack is you have extension authors that somehow trick users into installing these malicious extensions, either by having the user sideload them, or perhaps managing to get your malicious extension into a centralized repository, And this gives you a very powerful vantage point, as we were just talking about. Extensions can do a lot, and so you are able to do these, so-called man-in-the-browser attacks, right? You don't need to worry about TLS. You can just kind of sit there and wait for the user to give you some sensitive information, or even indeed, you could imagine browser-based botnets, right? You can take advantage of the resources provided by these machines. So lots of different attacks you can do. They're easy to develop, right? So we're talking about web technology, so if you know some JavaScript and you can read some browser documentation, then you're well on your way to developing these sorts of attacks. And they're difficult to detect, right? So I partially come from a background of static and dynamic analysis, right? And so JavaScript is notorious for being difficult to statically analyze on the one hand, and on the other, being a highly dynamic environment, all of the normal coverage problems that you have with dynamic analysis are only exacerbated by the web setting. So there's a ton of problems and a ton of threats. Of course, the sky isn't yet at the point of falling, and so we do have some existing methods for protection, and there's a rich literature on this. But I'll just point out two, the broad strokes of two big approaches. So first of all, we have browser extension marketplaces, right? And if you're familiar with the mobile space, this should be very familiar to you. So think Google Play for Android or the App Store for iOS. So these central marketplaces are actually great for security. You trade off a bit of freedom, but at the same time you have one centralized place where a vendor can go and do all sorts of different security analyses, and then certify in some way that, hey, these extensions that you find here, or this code that you find here, is guaranteed to be benign. Well, guaranteed is highly likely to be benign. So what does that mean in the extension context? Well, that means some sort of automated analysis. That could mean some sort of human review. Perhaps some extension signing and or forcing users to use this channel to install this third-party code. But this combination of automated analysis and manual review and extension signing is really the vetting model that underpins all of Firefox extension security. If something goes wrong with this vetting process, then all bets are off. So hold that thought. I will also say that there is kind of this alternate approach based on extension isolation. And so if you're familiar with the Chromium security architecture, this is essentially that, where the idea is to first isolate extensions from each other and then lower the amount of privilege in each of these extension compartments to the least amount needed for them to work correctly. At least that's the idea, and maybe have some policy-based enforcement on top of this. So that works quite well, although it's really intended for this benign but buggy model and not really so much for the malicious extension model. And so there's a lot of work showing that, well, extensions or mobile apps can request all the permissions and users will just say yes, 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 yes. And so this is not a panacea, but it does, help to prevent some of the attacks that we'll talk about. But Mozilla really doesn't have this yet. On that note, just to contradict what I just said. So Mozilla does have this idea of that, well, this proposal for the add-on SDK, also known as Jetpack, if you're familiar with that terminology. This is something they introduced back in 2009. So it's been around for a while, and it indeed, gives extension authors and users some of the security primitives that you would like to have in a modern browser extension framework. So, for instance, it isolates extensions from each other. You have this idea borrowed from Chrome where you have separate content scripts that interact and are exposed to web origins on the one hand, and core scripts that have access to the browser API, and then a very narrow IPC channel for these two things to communicate with each other, which, in this model, the attacker has to somehow bridge this channel in order to gain access to the privileged browser API. So this is a much better situation and really, implements this idea, well, has the potential for implementing this idea of least privilege. However, unfortunately, adoption has been slowed, right? So it was introduced back in 2009, And if you look at the progression over time, well, at least since we started measuring this, back in October 2014, looking at the top 2,000 extensions in the Mozilla add-on store, you'll find, well, there were only 12% of extensions that were actually using Jetpack. And so, well, maybe things would get better over time, but, we looked at this again, a year and a half or so later, and in March 2016, you saw only a modest increase, right? Less than a quarter of extensions were using this new, more secure extension framework, whereas the vast majority was still using this very insecure legacy architecture. And indeed, many people view Jetpack as a bit of a failure, right? So these days, or at least, recently, it was announced that Mozilla was going to supersede this old Jetpack architecture with web extensions, which is essentially the same thing as, well, it's a source compatible or API compatible version of Chrome extensions. So, that is targeted for release in Q3 2016. But again, the majority of extensions out there in the wild are still using this insecure architecture. So, let's see what's possible. So I'm going to dive straight into the attack model, right? So this is kind of the idea. Let's say you're a veteran at Mozilla, and somebody has submitted this extension to you, and they don't have this nice label that says, hey, I'm an evil extension. And so, they're running it in their vetting sandbox, and, they're going to run some automated analysis on this and perhaps a manual analysis. And primarily what they're going to be looking for, aside from, different programming practice guidelines, are, is this thing executing any sensitive calls? Is it doing any kind of string evaluation for code? Is it accessing the file system? Is it accessing the network, et cetera, right? And there's a well-defined list of XPCOM APIs that give you this sort of thing. And they'll find, okay, there's nothing in here that does this, and so we'll assume, okay, it's labeled benign and gets published in the App Store or the extension store. Okay, so let's say a user downloads this. Then what happens? Something like this. Okay, we have the same extension, but now it's running in a user's browser. And so now it's co-inhabiting that browser with other extensions, other benign extensions. But these other benign extensions might be performing some sensitive calls, right? Some security relevant calls like accessing the network or file system, which this evil extension can then use, right? So we have this kind of situation where extension X and extension Y are leaking capabilities to this evil extension that it can abuse to implement an attack, even though it itself doesn't contain any sensitive calls. And so this is the basic idea behind extension reuse attacks. We have the appearance of a benign extension, but it's actually malicious, and it's difficult to tell during vetting that this is actually occurring. So what's the impact of all of this? Well, some key takeaway points. The lack of isolation leaves legacy extensions basically defenseless against these capability leaks. These legacy extensions are not written to kind of shield the capabilities that they contain from, other extensions. So there's a lot of vulnerabilities out there, as we'll see. Attackers can really automatically find and stitch together these exploits by abusing capabilities. And so this is kind of an analog of, these return in the libc style attacks that you see in the binary world. We're finding capabilities and kind of stringing them together to implement our attack. And, kind of in the nice tradition of Aikido, right, the more power these vulnerable extensions have, the easier it is for an evil extension, right? So the richer the ambient authority kind of living in the browser, the more complex and powerful attacks we can create. So if we wanted to execute some sort of attack in a straightforward way without, the technique that we just saw, what might it look like? Well, let's say we wanted to implement a classic malware dropper. We're going to reach out to the network and pull down some resource, drop it to the file system, and execute it. How would that look like using the XPCOM API? Well, it would look something like this. So this is a lot of boilerplate to kind of execute the workflow that I just described. But essentially, for someone who's experienced in vetting Firefox extensions, it's very easy to see what's going on here. You're invoking some XPCOM APIs to, again, reach out to the network, download some code, and launch it. So this is really straightforward and easy for a vetter to kind of flag is malicious. So how would it look instead? Well, for an evil extension and two extensions X and Y, we can implement this attack, very easily. If we wanted to download, we would find in this extension X, okay, it exposes this download capability, maybe via something like this, right? So this is an example actually of code that's exposed by a real extension that we can exercise in this way, where we give it an array of file objects that describe where we want to get the code from and where to download it. And then we simply invoke that capability in this other extension. So we can do that, reach out to the internet, get that exe and drop it to the file system. And then, in this other extension Y, invoke some functionality that's intended to launch an editor. But in this case, we target it at the exe that we just dropped and go ahead and launch that. So again, none of these sensitive calls were actually in that extension. We just took advantage of stuff that was in our namespace. So, on the question, to paraphrase Shakespeare, to reuse or not to reuse, for a malware author, it's pretty obvious which one of these is going to pass vetting, which again is really the only thing preventing this sort of attack from occurring in the Firefox ecosystem. The one on the right, it's much less obvious what's going on, which, we'll see some empirical evidence for this fact later on. Just as another example to demonstrate some generality, let's imagine that we want to implement a keylogger, which is going to send every key press that the user makes in the browser to evil.com. How can we do this? Well, fairly straightforwardly. This is an example abusing another real extension that anyone can download and install from the Mozilla App Store. So here, this is an extension that provides a dictionary or Wiktionary lookup service, and the malicious extension is simply going to reach out to some property defined in this vulnerable extension and set it to an attacker-controlled URL, and then register a key press event handler that is going to get invoked every time a key press event is created, and then send the corresponding key to the attacker. So maybe not the most efficient way to implement this attack, but it kind of gets the point across. So exactly, sending a bunch of keystrokes to evil.com. So those are extension reuse attacks at a high level, and I'm going to turn it over to Ahmet now to give you a flavor for how this actually looks in practice.
So there are some challenges about finding these vulnerabilities because there are hundreds, thousands lines of code, JavaScript code, and finding these things, security-sensitive functions, and you also have to find the security-sensitive functions that you can control from outside. You can give some malicious parameters arguments to them, and you can turn these capability leaks into some attacks. So it is like looking a needle in a haystack. So it is a little difficult. To make it easier, we implemented Crossfire, which is a lightweight JavaScript static analyzer and also automated exploit generator. So it gets the JavaScript file or a directory of JavaScript files as an input, and then it parses these JavaScript files. It turns them into abstract syntax trees, and it does the analysis over this syntax tree. It traverses the code, and it consists of two stages. In the first stage, it discovers the code, looks at the code and determines what are the global variables, what are the global functions that can be exploitable, and looks at the security-sensitive functions that can be exploitable. And it generates the call graph. In the second stage, it finds the paths from these global functions or variables to the entry points to our sinks, which are security-sensitive functions. And after this, it generates a vulnerability report, which is given to the exploit generator. And exploit generator has predefined exploit rules. These rules are predefined for each type of security-sensitive function. it combines the vulnerability report and exploit rules and generates the exploit. Now I will do a demo to demonstrate how does it work. So here is a simple JavaScript code which has a global variable, global function, and a global object.
Sorry, it's not on the screen.
Oh. Why it is not? Okay. Yeah. Sorry. So in this example, you can see the function, global variable, global function, and global object. It also has some functions in it. And since the object is global, everything inside the object is also global and can be accessed by outside. And here is the AST representation of this code. AST representation is much longer, like 10 times larger than the exact code, but it gives us very structured form of the code. So it does the parsing and everything, and at the end we get very well structured form of the code, and then we do the analysis. So I will show you. So this code doesn't have any thing inside of it. So also I need to move this and re-execute it. It doesn't have any thing inside of it. It just has some global functions. So what it gets is just give some statics to us about the code. But in the second example, here we see two functions. In the first function, it gets two parameters, and it uses first parameter as the pet of the file, and then it executes that file. In the second function, it calls the first function, but the parameters are in reverse order. So you see the second parameter of the second function actually given as the pet name. And there is also another thing, but this thing is different because, as you see, this thing does not get any parameter from outside. It just has some static value, and it is not possible to tamper this function to use it as an attack. So when we execute the code for the second example, so you see the sync found in line 4, and it generated two exploits. One is the function f1 with malicious parameter. This is the file, or full path of the file. And the second one is the second function, but the parameter, the order, you give the file path in the second parameter. So let's look at another example. In this code, a global variable is defined, which points to a file path or a binary file. And then there is a function which has a local variable, but it gets a global variable. So we use data tainting with this tainting operation. We taint this local variable with the global variable, and then we follow the path of this variable. This goes to the sink, And when we execute the analyzer, it gives you which variable that you need to modify and then execute the function. So, yeah, these are very easy examples just to give you the idea of how it works and what kind of things it does, it considers. So this example a little bit different because in this one the codes are taken from a real extension. It looks very complex, so I don't expect you to try to understand it. But let's give it a try. And here we found different things. These are the functions that goes to those things, and these are the attacks that generated. And now, instead of a file, I will give this a folder, an extension folder. So this is also a real extension from the Firefox extension store. And it looks at each JavaScript file inside this folder and finds the vulnerabilities. So this is the folder. So here you see it found two different exploits. One open URL in tab and other one also a network access type of vulnerability. And I will also show you how you can verify that these attacks work. So I will open the Firefox browser. A secretpet can be used to demonstrate these examples. Instead of writing an extension, we can just simply execute the code here. And let's look at what we found. I didn't copy it completely correct. Okay, so you see a tab is opened and it connected to this web page. And in another example, so here there is a problem. It is not, here it sets the object, so it will not work. It is obvious. The reason why it shows it is due to our tainting principles. When we taint it with the object name. So now the user needs to look at the code and try to do some modification to make it work. it shows us the sync function, security function. It says 172. And when you look at this code, you easily see that this is the parameter that goes to this @tab function, and it is set by the property of that object. So the only thing you need to do is just copy it. And it opens the tab. So I think this demonstrates how the tool works and how the output of the tool can be used for generating attack. So once you get these exploits, you can do any combination of them to make more sophisticated attack. You can download binaries, execute them, or do different types of attacks together. So we also evaluate that tool, and we used 2 different experiments. In the first one, we look at the top 10 most downloaded extensions, and we manually analyzed all of them to verify that our output is correct or not. And in the second experiment, we look at the top 2,000 most downloaded extensions, and we, since it is impossible to manually verify all of them, we selected a random set, 300 to 23 extensions, so which is 95% confidence level and 5% confidence interval, and we did analysis, manual analysis on those. And we also performed a case study. We developed an extension which has the cross extension call in it, and we submitted this to Firefox extension marketplace, and we applied for the full review, which is the highest level that you can get from the reviews, highest level of security. So the top 10 Firefox extensions, now you see the extension names. Probably many of them are familiar to you, like NoScript or GreaseMonkey. And you see the number of automated exploits, which means we didn't do any modification. We just copied the code from the tool and passed it, and it worked. And the manual exploits, where we did some manual modification to turn them into working exploits. And the false positives, that sometimes tool finds something, but actually there are some complex conditional checks, some sanity checks before it goes to the sync rank. It becomes impossible to exploit using that function. So these are our false positives, and at the end you see the number of users. As you see, they have millions of users. So this is from the random set, and we found 255 working exploits, and when we look at these working exploits, 20% of them were actually automated. They didn't need any change, any modification, and the rest of them required some kind of modification. So what were those positive vulnerabilities? So they were, majority of them were network access vulnerabilities, but also a significant number of file access, file I/O, and event listener registration. And for the event listeners, we didn't look at any event listening type of thing. We just focus on the keylogging events because they are the most dangerous ones that can easily turn into keyloggers. And they have some preference access and code execution type of vulnerabilities as well. So the performance. The Crossfire is a lightweight tool, so it's a very fast static analysis tool. We measured the time of the tool per extension, and we find out it just takes 1 second on average to analyze an extension. So there was one exception which took 763 seconds, and it was the extension called local load, which has the local copies of all the famous JavaScript libraries like jQuery or other type of libraries with 10,000 lines of code. So it took for a while, but it was still very fast compared to other existing static analysis tools. And we also measured the time spent for the user to verify that the exploit is working, or the time to modify the output to look at the template and turn it into a working exploit, the time spent for this. And we found out that on average it just takes 6 minutes per exploit to verify it or to use the template and to make it a working exploit. So this is not also making an attack which can combine many of those capabilities or exploits together. It is just one type of operation that we call exploit here. So for the ethical reasons, it was impossible for us to make a scientific evaluation in the real world of this attack to show that it can evade the existing detection techniques. But what we did is we developed an extension called Validate This Website. It was a very simple extension. It just, when user clicks a button, it just does the markup validation of the web page using an online markup validation service. So it was just 50 lines of code. But we embedded a cross extension call inside that extension, and it is a function call to NoScript extension, which is a very popular extension, and it connects to a URL given, but in a stealth manner. It doesn't open a tab, so the user will not notified about that. It just does the connection in the background. And we submitted this extension to the Mozilla Web Store, and we applied for the full review. Also, there is one thing I would like to tell you. We registered the domain name for this purpose, but we didn't put any content on it. So it was unnecessary harmless link. And we get full review, and we didn't receive any security warning. The reason for that was it wasn't that the vetters are not do good reviews, or they do really an amazing job. They look at the code very carefully, or they use some automated tools to find out these problems inside the extension. They execute the extension and they verify that extension does what it claims in the description of the extension. So they really do a very good job, but they weren't aware of this type of attacks, so they weren't checking this. Also, their automated tools didn't highlight any problem in the code, so they probably didn't notice that can be a problem. And we received some best practices type of comments, but we didn't receive any security warning. And once it is accepted, we downloaded the extension and we verified that this cross extension call works. And then we removed the extension immediately from the web store. So for the limitations, Crossfire is not designed to be to show the absence of the vulnerabilities, but instead it is designed to find the existence of the vulnerabilities. So it is not a sound and precise analysis tool. And it doesn't handle inferring dynamic data types or prototype-based inheritance. And it doesn't handle the string evaluation that you can, if you have anything in eval function or set timeout function, any string, code, it doesn't evaluate them. But as you see, these limitations doesn't prevent to find hundreds of exploits. And without making a sound tool, we trade off this soundness, precision with the performance, and at the end we had a very fast tool which can easily find these exploits and vulnerabilities. So for the mitigation and detection, what we can do is, the first thing we can do is the isolation. It is very important, and now the modern extension architectures introduced very good isolation. For the Firefox, they haven't migrated yet, but probably they will. But isolation is also not completely solves the problem. So there are also other things that we need to do. The least privilege is another thing to mitigate these problems. When you have the least privilege, then even if a vulnerable extension exposes some functionality, the evil extension, malicious extension, can just have this privilege of the vulnerable extension, and it may not harm the user a lot. So it is bounded by the privilege of the vulnerable extension. Secure functionality and data sharing. So the extensions can be isolated, but they may also need to share some data and functionality. And if we don't do it correctly, then it may still cause this extension reuse vulnerabilities and attacks. For example, we also look at the Jetpack extensions. Yes, the attack surface was very narrow, but then also it was easier to find the vulnerabilities, because in the Jetpack you explicitly export a variable or functionality, and since these extension developers are not educated in the security, they may sometimes expose some security critical function. They may export these functions, and you can still do code extension reuse attacks on these Jetpack extensions. They are not completely immune. So another thing we can do is we can use some static analysis similar to Crossfire, maybe much sounder, precise JavaScript static analysis to find these vulnerabilities. And when we see any vulnerabilities, maybe we can send it to the extension writer to correct them, check them. In addition to those things, we also contact with Mozilla security team, and we inform them about these vulnerabilities. So now they educated their vetters, and we don't expect to see this kind of attacks in the wild anymore, but it is not also, there is always human error in the process. So for the conclusions, I will hand over to Will.
Okay, thank you. So to wrap up, there are a few key takeaways that we want to leave you with, right? So first of all, this lack of isolation really is a huge problem. And so, it's long been recognized that you should, as Ahmet and I were both saying, this is kind of a keystone, right, foundation for building a more secure browser. And so this is something that Mozilla really needs to, develop, and luckily they are on that path. The second key takeaway, though, is that for now, these vulnerabilities are exploitable. And we showed that attackers can very easily automate this, so it's, even though, it's a combinatorial problem of, knowing which extensions a user will have and all of this. I mean, if you have some intelligence on, what your target population is likely to have, or you're targeting a particular individual, and you can extract this information, then it's very easy to automate the process of finding these leaked capabilities and linking them together. So, as a final takeaway, we really need this combination of this robust isolation that hopefully will be forthcoming in a future process isolated electrolysis enabled Firefox version with a modern extension architecture. Hopefully we will have better vetting because these isolation techniques help, but they don't really solve the entire problem. Malicious extensions are still an issue, and so we still need some kind of vetting or perhaps community feedback and crowdsourcing of security judgments. As well as better analyses, right? So hopefully something like Crossfire integrated into the existing suite of JavaScript security analysis tools out there to help find and remove malicious extensions from these marketplaces. So with that, we'd like to conclude, and we'd be happy to answer any questions you might have.
Yes, for the obfuscated code, the tool can still work, but for the output, when you look at the output, you may not understand it, what type of vulnerability is it. So the tool still finds the paths from the sources, global variables or global functions to the security-sensitive function calls, but then in the human analysis, you may need to spend a bit more time, but it works for the obfuscated code.
So I'll actually tag on to that answer as well. So you're right that malicious JavaScript is often obfuscated, right? And indeed, they could be using features like string evaluation or assembling, the source code from arrays and all of this to make it, the job of a tool very difficult. The thing is, if you submit an extension like that to Mozilla, they're going to reject it, right? So obfuscated, there's only so far you can go in terms of obfuscation. And indeed, that's why we structured our case study in a way where we didn't obfuscate anything, because that's actually highly suspicious. So, just to qualify that.
But for some commercial type of libraries, sometimes they can be obfuscated in the extension code, but yeah, it is not very common.
It's not very common.
Mm-hmm.
So from about 2,000 apps that you analyzed, do you find how many?
I didn't measure the obfuscated ones because it wasn't really affecting the code. I just... I don't remember any obfuscated ones from the top 10. Yes. Yes, please.
You take a look whether current extensions actually use this cross-scripting using code other extensions. Is it a common technique, or is it something that's actually used, or is it not used at all? So could you just implement isolation and all the extensions would still work?
There might be very rare cases where they need to use those things, or sometimes they may need to use some functionality of the browser. So you cannot just isolate the legacy extensions and make them work. So there will be some broken functionality. But if you look at the interaction between extension to extension, then it is very rare. Maybe one case or two cases among the 2,000 ones.
Yeah, so I agree. It's very rare, and it's not something that I think is directly supported by the browser vendor. But in kind of thinking ahead, right, like with this movement to make browsers kind of like the new operating system, you can easily imagine like extensions wanting to provide like library type services. And so if you have complete isolation, then that becomes very difficult, right? And so I think it's actually very interesting to think about what a secure way to do this might look like. And I think a start of that might be to think about, okay, well, we have post message, right, already available to do message passing. And so, if you start with this, maybe you can do something good, but then you have to think about, I don't know, I'm not sure. We haven't fully thought it through, but it could be an interesting direction to kind of, make the browser more like an operating system and have third-party libraries kind of exist in the browser instead of having to reach out to the network and download a bunch of libraries.
Another? Yes, please.
Do you find any malicious extension that is actually in
That is using this extension code reuse attack. No, we didn't actually look at them, but for the ones that I did the manual analysis, I didn't see.
You mentioned, sorry, Darren Boyd from the Register, you mentioned that you went and told Mozilla of all of this, and so kind of that their way that they're going to go forward is to sort of vet, be more rigorous in the vetting. Is there, I don't know, I mean, now that information would be out there, how do you, would you see that those sort of the code reuse attacks are going to, would you expect them to be used now? And do you think that that's going to result in, I don't know, sort of challenge Mozilla's vetting?
Yes, it can challenge, but since now they are informed about these things and now the vendors expect those type of things, now probably it will be very difficult to see it in the wild, but if there is a human error that cannot be controlled, then yeah, it can pass the vetting process and it's possible, but not very likely.
Yeah, just to comment on that as well, I think it's going to be interesting to see what happens. So, in the interim, before they roll out web extensions, you might see people try to do this, and then that's kind of the trade-off of doing attack research, right? You're kind of publishing attacks, and people could try to do it. So, using our tools, one way that they might, try to ameliorate this a bit, you can actually think of other approaches to this. So, for instance, maybe instrumenting the browser to, record failed API invocations, which would represent like one extension trying to reach out to another extension that it hopes is present. And, so a dynamic analysis might be another way to kind of address this. It's not something we looked at, but, it's something that either we have or we might suggest to them. Okay, well, if there aren't any further questions, then, thanks for showing up.